In this video, we're going to learn about Descartes' rule of signs. It's a very clever little idea where it says let p of x be a polynomial with real coefficients written in standard form. Now, the number of positive real roots to that equation, p of x equals 0, is either equal to the number of sign changes between consecutive coefficients of the polynomial or is less than that by an even number. And for negatives, the negative real roots of the equation p of x equals 0 is either equal to the number of sign changes between consecutive coefficients of p of negative x or is less than that by an even number. Now, what does this necessarily mean? Let me break down this in one of the problems. So let's look at, this is a polynomial written in standard form. Let's look at the coefficients of this polynomial. They are positive 1, negative 3, negative 4, 2, and positive 4. Now I'm going to start with the constants at the far right, and I'll explain why in just a second. But we're going to count how many times does the sign change. So from 2 to 4, no sign change. Now from 2 to negative 4, there is one sign change, so I'm going to mark that there is one sign change. From negative 4 to negative 3, nothing changed, so I'm still at one sign change. And then from negative 3 to 1, there was another sign change, bringing my count up to two sign changes as I went consecutively through all my terms in standard form. So what this tells me is that there are possibly two positive real roots, or maybe even 0 real roots. The reason why it changes by 2 is that sometimes roots come in conjugate pairs, especially the complex ones which aren't real. They always come in conjugate pairs for polynomials with real coefficients, as you saw in the conjugate root theorem. So we're taking into consideration there might be two complex roots instead of two positive real roots. Now, what could this mean? The reason why I'm saying this is if I look at the end behavior of this polynomial, which is a positive odd term, so the end behavior should be down to the left and up to the right. If I know for a fact the y-intercept is 4, I know it has to end by going up to the right. But let's build up this polynomial from the smallest degree term to the biggest term and see what dictates its behavior. Now, 4 by itself keeps it above the x-axis. So we know that for sure. That doesn't help us find any of these roots. But now let's look at the next term with it. So 2x plus 4. Now 2x plus 4, if I'm going to the right, we'll start with positive x's since this tells us about positive real roots. We'll just consider all the positive ones. Then if I plug in positive values for x, will 2x plus 4 ever be negative? No. That'll continue to always be positive. I'll even mark it here with a positive symbol next to it. So there's no way for me to cross the x-axis yet. But now when I consider the next term, the negative 4x squared, plus 2x plus 4. Now, since this is the biggest term for bigger values of x, this will end up being a negative value. So there's a chance that with this term, my polynomial can go below the x-axis, into the negatives below it. Because now I'm considering this negative 4x term. If I continue to go down, check the next one, negative 3x cubed, there's even more of a chance that it's going to stay negative because now two of these terms that are big powers are fighting against these two other terms that are positive positive terms with these two negative ones. So overall, if x was big, this would be a negative number. And then we consider the last term, x to the fifth, which determines the end behavior. With x to the fifth, it's going to end up being positive for sure. So even though I got to the negatives, it definitely comes back up. So there's two possible spots where I could have a root for the equation. There's also the possibility that these two terms can't beat out the x to the fifth because of how positive it is. And there is a small chance or a big chance that it just curves up anyway earlier and never crosses the x-axis. Now let's look at for the negative side. So here we'll still say x is this positive value, but now we're going to force it to be negative by putting a negative out in front. So how that changes the polynomial is now I have like negative x to the fifth minus 3 times negative x to the third minus 4 times negative x squared plus 2 times negative x, then plus 4. So we're going to see how negatives are affected by these powers and see if that changes this little step here. So I have negative x to the fifth, which will simplify. If you raise a negative number to the fifth power, it is a negative number. Over here, same thing with a cube. If you raise a negative number to a cubed power, it becomes negative. So a negative times a negative makes that positive. And over here, whenever you square a negative number, it becomes positive. So it remains negative 4x squared. And then 2 times negative x is negative 2x, then plus 4. And again, we're going to count those sign changes. So as we go from the left to right, from right to left, forward to negative 2, that's a sign change. So that's the first one. Then negative 2 to 4, no sign change. So I still only have one sign change. From negative 4 to 3, that's another sign change, so I have 2 of them. And then from 3 to negative 1, it's another sign change, so I have 3 sign changes, which tells me there are either 3 or less than that by an even number, or 1 negative real roots. So again, if I use that same logic that I used over here, building up this equation right here to understand it, starting with 4, that is just a positive number, so I should stay above it. I know that one to be a fact. Now, when I look at negative 2x plus 4, now, since I have that negative 2x, that will be out that 4 for a big enough x value, so there's a chance that it becomes negative from here. So if I'm here, it might dip below, and I might have 1 right there. Now, as I continue, as I add on the negative 4x squared minus 2x plus 4, this is still negative, so it kind of keeps me below the x-axis. But the next chance for it to come back up to the top is from this 3x to the third power. With 3x to the third power, that entire polynomial has a chance to become positive. So even though I'm below, there's a chance it can come back up. But at the end of the day, with negative x to the fifth, we already knew this from the end behavior. It's definitely going to end by going down. So there's 3 possible spots for it to cross, or there's the potential that it never comes back up. It just continues to go downwards anyways, and you only see it cross once. Now let's look at a graph of this to see if these predictions are correct. So if I were to graph this polynomial, you'll see here that it crosses 2 times on the right side, so 2 positive real roots, but only 1 negative real roots. So what that tells me is that the other 2 roots are going to be complex or imaginary. But let's put this into practice. So that's the why behind how this works. But let's actually see what we get. So we're going to say, what does Descartes' rule of signs say about the positive real roots and negative real roots for each polynomial function? So looking at this, this is p of x, so we'll assume like x is positive. We'll count the number of sign changes. From 1 to negative x squared, that's from positive to negative, that's the 1 change. From negative x squared to x to the third, it's another sign change. So there's 2 sign changes. So that's going to be 2 or 0. Again, you go down by an even number until you can't go down anymore. Or 0 positive real roots. And then if I were to plug in a negative number, so p of negative x, giving me negative x cubed minus negative x squared plus 1, I get negative x cubed. This is now still a minus x squared, because the squared keeps that positive, so it's still minus plus 1. And counting these sign changes, there's one change from 1 to negative x squared, but there's no change from negative x squared to negative x cubed, so it's just one change overall. So there's one negative real roots. So as you kind of saw earlier, there's a guaranteed negative real root. So we will for sure have at least one root into this quadratic, for sure. There might be no positive real roots, or there might be two, but we know for sure we'll have one negative one. So if we're using the rational root theorem, we might want to check the negative roots first, because that will definitely lead to an answer, while the positive ones might not, because there could be 0 positive roots. So let's try practicing this again. From 1 to negative 5, that's one change. From negative 5 to 2, it's another change. And then no change from 2 to 8. So there's 2 or 0 positive real roots. And another quick way you can go through all these terms for this next part for p of negative x is if the power is odd, you'll see a sign change. The power is even, you won't see a sign change. And for the constant, the sign will never change. As you saw earlier, that's kind of like a fixed point for understanding all the possibilities. So for p of negative x, I'll have negative 8x cubed plus 2x squared. Don't change the positive even power. But then instead of negative 5x, I'll be plus 5x. Then plus 1. And going here, there's no sign change, no sign change, and then one sign change at the very end. So I have one negative real roots. Let's look at one more example. So here, starting from the end, no change. Then a sign change, so that's our first one, but then no change there. So just one positive real root. But for my negative real roots, p of negative x, that first, since it's an odd power, there's a sign change there. So 5x cubed. Don't change the x squared term. It doesn't change because of the negative. Then minus 9x plus 30. So I'm seeing here, there's one sign change, nothing changed there. Then something else changed. So there's two sign changes, leading me to 2 or 0 negative real roots. This would be very helpful for like trying to, like, if you had to guess a solution, it kind of directs you where to go first. Because if you have a guaranteed real one, you might want to check there first. Especially if you have one. That means that it won't be a radical, because those have to come in conjugate pairs. So there's probably some rational root that's going to work for it. And that is how you use Descartes' rule of signs.